While astronomers aim their telescopes at 3i Atlas, watching that kilometer-wide comet make its grand exit from our solar system, something far more extraordinary just happened that almost nobody noticed. Two objects from another star system didn't pass by Earth. They hit us. CNEOS 22 and CNEOS 25 survived a journey across the void that should have been impossible, punched through our atmosphere with forces that should have vaporized them, and crashed. One landed in the Barents Sea just days ago. Right now, fragments of extrasolar material are sitting on the Arctic seafloor, scattering with every current, burying deeper with every hour. Harvard's Avi Loeb has the coordinates. He has the data. What he doesn't have is time. Stay until the end, because this isn't about watching visitors leave anymore. This is about recovering what arrived before the ocean swallows the first physical evidence of another star system we've ever had the chance to hold. Subscribe and follow along, because what happened in the Barents Sea is just the first chapter. More objects are entering our atmosphere, burning through the sky while sensors try to separate solar system debris from interstellar arrivals. We can't predict which impacts will matter and which will fade into background noise. But CNEOS 22 and CNEOS 25 taught us something crucial. The window between discovery and loss closes faster than we expect, especially when the evidence is physical and the ocean is already claiming it. Right now, somewhere out beyond Neptune's orbit, a mountain made of ice and rock is leaving our solar system forever. Comet 3i Atlas, the third confirmed interstellar visitor we've ever recorded, is on its way out. Astronomers are watching it with every telescope they can aim in that direction. News outlets are running headlines. Amateur skywatchers are calculating exit trajectories. Everyone wants to know where it came from, how big it really is, what secrets it might carry about some distant stellar nursery we'll never see. We're obsessed with watching something leave. But while we were all looking up and out, tracking this cosmic farewell, something else happened. Two interstellar objects arrived. They didn't announce themselves with a glowing tail or a months-long approach that gave us time to prepare. They came in fast, burned bright, and vanished into our atmosphere before most people even knew they were here. One of them crashed into the Barents Sea just days ago. The other hit earlier this year. And unlike 3i Atlas, which we can only study from millions of miles away through the distortion of our telescopes, these objects physically interacted with Earth. They touched our air. They left debris. And if a team of researchers is correct, that debris might be the first recoverable matter from another star system in human history. This announcement came from Avi Loeb, the Harvard astronomer, who's become something of a controversial figure in recent years. You might remember him from the Oumuamua debates, or from his expedition to recover fragments of what he claimed was an interstellar meteor from the Pacific Ocean floor. Loeb has a habit of making claims that make other scientists uncomfortable. But this time, he's not alone. This time, he's backed by a newly calibrated data model, cross-referenced observations, and statistical analysis that's harder to dismiss. In February 2026, his team released findings that confirmed two objects, cataloged as CNEOS 22 and CNEOS 25, traveled here from beyond our solar system. Here's what makes this different from the usual interstellar visitor story. When we talk about Oumuamua, or Borisov, or 3i Atlas, we're talking about objects we detected while they were still far away, moving through space on hyperbolic trajectories. We see them coming. We watch them pass. We observe them leaving. They're lateral visitors, cruising through our neighborhood on paths that never quite intersect with anything solid. But CNEOS 22 and CNEOS 25 weren't detected by telescopes scanning the sky. They were detected by sensors designed to spot atmospheric entry events. These weren't things we watched fly by. These were things that came straight down. Think of it this way. Most interstellar objects are like cars passing through an intersection. You see them approach, you watch them cross, they drive away. But these two objects are more like skydivers who jumped from a plane you never saw, fell through the atmosphere too fast to track, and hit the ground before anyone could react. By the time the sensors registered what happened, it was already over. They didn't linger. They didn't give us time to aim cameras or prepare instruments. They arrived vertically, moving at speeds that turned them into fireballs, and then they were gone. CNEOS 22 impacted in the Barents Sea, north of Norway and Russia, in a region where the ocean sits on a shallow continental shelf. The water there is only 200 to 400 meters deep, which sounds like a lot until you compare it to the Pacific impact sites of other meteor events, where the ocean floor drops to 6 or 7,000 meters. Depth matters when you're trying to recover debris. In the Barents Sea, recovery isn't just theoretically possible, it's actually feasible with existing technology. But there's a problem. The Arctic is already redistributing that debris. Ice drift, sediment movement, biological activity, all of it working to scatter and bury whatever fragments survived the impact. Every day that passes makes recovery harder. This isn't like the telescope debates over whether Oumuamua was a comet or something else. This isn't about interpreting light curves or modeling outgassing. This is about physical matter, potentially sitting on the ocean floor right now, waiting to be analyzed in a lab. If Loeb's team is right, we're not just talking about confirming that interstellar objects exist. We already knew that. We're talking about holding one in our hands. We're talking about isotope ratios, mineral composition, structural analysis. We're talking about chemistry that formed around a star we can't even identify, carried across light years of empty space, and delivered to us by nothing but gravity and momentum. The stakes have changed. This is no longer a question of orbital mechanics and trajectory calculations. This is no longer about refining our models of how often interstellar objects pass through. This is about whether Earth has already received extrasolar material, and whether we're about to lose our chance to prove it forever. Because if nobody goes to the Barents Sea soon, if nobody drags the ocean floor and sieves through the sediment, this moment will pass. The debris will scatter. The trail will go cold, and we'll be left with data files and simulation results, arguing over numbers while the actual evidence dissolves into the Arctic. But before you dismiss this as another data glitch, another case of enthusiastic interpretation running ahead of careful science, something changed in 2025. This sounds like IM-1 all over again, doesn't it? A few years ago, Loeb claimed that a meteor detected in 2014, cataloged as CNEOS 2014-0108, was actually an interstellar object that hit near Papua New Guinea. He organized an expedition. He recovered metallic spherules from the ocean floor. He published papers. And the scientific community largely shrugged and said, maybe, but probably not. The problem wasn't that the claim was impossible. The problem was that the data was uncertain. Velocity measurements had error bars. Trajectory calculations depended on classified sensor information that nobody outside certain government agencies could verify. It was plausible, but not conclusive. And in science, plausible doesn't get you very far. So when Loeb's team announced CNEOS 22 and CNEOS 25, the immediate reaction from many astronomers was predictable skepticism. Here we go again. More hyperbolic claims based on noisy data. More extrapolation from limited sensor readings. More conclusions that outrun the evidence. Except this time, something is different. This time, there's a calibration model that didn't exist before. The CNEOS Fireball database is maintained by NASA and JPL. It catalogs atmospheric entry events detected by US government sensors, originally designed to monitor for nuclear test activity, but repurposed to track meteors. When a rock hits the atmosphere at high speed, it creates a flash of light and a burst of energy. Sensors pick up that signature. The database logs the event, records an estimated velocity, calculates a rough trajectory, and moves on. It's not designed for scientific research. It's a surveillance tool that scientists have learned to use as a secondary data source. And that creates problems. The raw sensor data is classified. What scientists get is a summary, a processed output that includes velocity estimates and impact coordinates, but not the underlying measurements. For years, researchers have worried about the uncertainty in those velocity estimates. If the velocity is wrong by even a small percentage, the difference between a solar system object and an interstellar object can vanish. Hyperbolic trajectories require specific speeds. If your measurement is too high, you might misclassify a normal meteor as something exotic. If it's too low, you might miss the real interstellar visitors entirely. For a long time, that uncertainty made CNEOS data interesting, but inconclusive. Then, in 2025, a team of researchers developed an empirical calibration model. They took CNEOS detections and cross-matched them with ground truth observations from independent meteor networks, places where cameras and radar actually tracked the same events. They compared what CNEOS reported to what independent instruments measured, and they found something useful. The errors weren't random, they followed patterns. More importantly, for events after 2018, the errors got smaller, much smaller. Whatever changes were made to the sensor system or the processing algorithms, the post-2018 data behaved differently. It fell into what the researchers called a low discrepancy regime, where the velocity estimates aligned closely with independent measurements. This matters because CNEOS 22 and CNEOS 25 both fall into this post-2018 window. They're not ancient data points from a less reliable era. They're recent detections, recorded by systems that now show consistent accuracy when tested against independent sources. But calibration alone doesn't prove interstellar origin. You need more than accurate velocity measurements. You need to show that the uncertainty doesn't matter. That even if you introduce noise, even if you assume the worst-case errors, the conclusion still holds. That's where the Monte Carlo simulations come in. Imagine running the same atmospheric entry event 1,000,000 times, but each time you add random noise to the velocity measurement. You let the numbers jitter around within the error bars. You simulate what happens if the sensor was slightly wrong in 1,000 different ways. Then you check how many of those million simulations produce a trajectory that could belong to a solar system object bound to the sun's gravity. For CNEOS 22, the answer was 0. For CNEOS 25, the answer was 0. 1,000,000 simulations per object. 0 bound orbits. In statistical terms, these objects are outliers at a level that goes beyond normal measurement uncertainty. The sigma values, which measure how many standard deviations away from normal something is, place both objects in a range where the model would have to be catastrophically wrong for the conclusion to flip. Not slightly wrong, not kind of wrong, completely, fundamentally broken in ways that would show up in every other detection too. And it doesn't. The model works for everything else. It only breaks if you force these two objects to be solar system members. Now, this does not prove composition. It doesn't tell us what these objects were made of, whether they were rock, or ice, or metal, or something we've never seen before. It doesn't tell us which star they came from, or how long they traveled, or why they ended up here. It absolutely doesn't tell us whether they're natural or artificial, and anyone who claims it does is overreaching. What it does tell us, with a confidence level that's hard to ignore, is that these trajectories do not belong to our solar system. They came from somewhere else. But then something strange shows up in the numbers. When Oumuamua passed through our solar system in 2017, it was moving at about 26 kilometers per second relative to the sun. That's fast. That's the kind of speed you expect from an object that's not bound by our star's gravity. something just passing through on its way from one part of the galaxy to another. Comet 2 I/Borisov, which arrived in 2019, was even faster at around 32 kilometers per second. And 3I Atlas, the object everyone's currently obsessed with, is screaming out of here at roughly 58 kilometers per second. These are the speeds of interstellar travel. These are the velocities that match our models of how objects move between stars. So when you look at CNEOS 22, moving at about 21.5 kilometers per second, and CNEOS 25 at roughly 16.9 kilometers per second, something feels off. They're slower, significantly slower. In fact, CNEOS 25 is barely faster than Earth's own orbital velocity around the Sun, which sits at about 30 kilometers per second. If you're trying to escape a star's gravity and coast across interstellar space, you'd expect to pick up speed, not slow down. Yet, here we have two objects that are definitively interstellar by every trajectory analysis, but moving at speeds that seem almost leisurely by interstellar standards. This creates a paradox. They have the orbital characteristics of interstellar objects, trajectories that can't be explained by solar system origins. But they have the velocities of objects that shouldn't have made it very far. It's like finding a car on the highway with out-of-state plates and a destination 2,000 miles away, but it's only doing 30 miles per hour. It'll get there eventually, but something about the picture doesn't quite fit. The mainstream interpretation is detection bias. Maybe interstellar space is full of objects moving at all different speeds, but we can only detect the slower ones. Faster objects might disintegrate too quickly in the atmosphere, turning into vapor before sensors can get a good reading. Or maybe they hit with so much energy that the signature gets misclassified as something else entirely. If that's true, then CNEOS 22 and CNEOS 25 aren't anomalies. They're just the only ones slow enough to survive detection. The faster ones are out there, burning up unnoticed, contributing to atmospheric chemistry we haven't connected to interstellar sources. But there's another interpretation, one that's more astrophysically interesting. Galactic velocity is not uniform. Stars move in streams and clusters, groups that share similar trajectories through the Milky Way. If CNEOS 22 and CNEOS 25 originated from stars that are co-moving with our Sun, stars that happen to be traveling in roughly the same direction at roughly the same speed, then the relative velocity would naturally be lower. It's the same reason why cars on a highway don't seem to be going that fast relative to each other, even though they're all moving at 70 miles per hour relative to the ground. If these objects came from nearby stellar neighbors that are keeping pace with us in galactic terms, slow speeds wouldn't be a paradox. They'd be expected. And then there's a third interpretation, one that edges into speculation, but can't quite be dismissed. What if these objects didn't just happen to arrive at low speeds? What if something influenced their trajectories? Not intelligence necessarily, not targeting or intent, but gravitational shepherding, interactions with other bodies during their journey that nudged them into capture-friendly orbits. The galaxy is full of dark matter, rogue planets, stellar remnants. An object crossing interstellar space doesn't travel through empty void. It travels through a gravitational landscape that can bend and redirect its path in subtle ways. If you run enough simulations of interstellar trajectories, you start to see patterns. Certain speeds and angles are more likely to result in close encounters. Certain configurations favor arrival over flyby. There's no evidence for intentional targeting here. None. But there is a pattern tension, a mismatch between what we expect interstellar objects to do and what these particular objects appear to have done. Are we misunderstanding interstellar flux at small scales? Are meter-sized objects fundamentally different from kilometer-sized comets in ways we haven't accounted for? Or are we just seeing statistical noise a couple of outliers that happen to fall outside our current model parameters, but don't actually mean anything deeper. We don't know yet. And that uncertainty is where the real science lives. But velocity isn't the only thing that doesn't add up. When a rock hits Earth's atmosphere at 20 kilometers per second, the air in front of it doesn't have time to move out of the way. It compresses. It heats up. It turns into a plasma that's hotter than the surface of the sun. And that superheated air pushes back against the rock with a force called ram pressure. For small objects measured in meters instead of kilometers, this pressure is usually enough to shatter them completely. They fragment into dozens or hundreds of smaller pieces, which then fragment again until what reaches the ground is either dust or a scattered field of tiny debris. Most meteors don't survive intact. Most meteors don't make it to the surface at all. Ceneos 22 experienced ram pressure of approximately 5.2 megapascals during its atmospheric entry. Ceneos 25 endured around 1.5 megapascals. To put that in perspective, 5 megapascals is about 50 times atmospheric pressure at sea level. It's the kind of force that would crush a car. It's the kind of stress that turns ordinary rock into gravel. And yet, based on the energy signature and the trajectory data, both objects appear to have survived deep into the atmosphere before finally breaking apart. They didn't shatter immediately on contact. They held together. This raises a question about composition. Ordinary stony meteoroids, the kind of rocky fragments that break off asteroids in our own solar system, typically fragment at pressures between 0.5 megapascal and 2 megapascals. Iron meteoroids are tougher, surviving up to 10 megapascals or more because metal can handle stress better than rock. But even iron has limits. And meter-scale objects are particularly vulnerable because they don't have the mass to absorb and distribute the stress. They're small enough that structural flaws can propagate through the entire body almost instantly. So, what were CNEOS 22 and CNEOS 25 made of? Were they iron-rich, chunks of some extrasolar protoplanetary core that got ejected during a collision and wandered the galaxy for millions of years before finding Earth? Were they made of some kind of composite material, layered or structured in ways that gave them extra strength? Or were they just lucky, objects that happened to have the right internal configuration to survive pressures that should have destroyed them? There's also the IM-1 comparison. The 2014 meteor that Loeb claimed was interstellar reportedly survived pressures exceeding 100 megapascals, which would make it one of the toughest objects ever recorded. That level of strength suggests either unusual composition or unusual structure, something beyond typical meteoroid materials. If CNEOS 22 and CNEOS 25 are related to IM-1 in any way, if they're part of a population of unusually robust interstellar objects, then we're looking at a pattern. Not just one outlier, but potentially a class of material that behaves differently from what we're used to. Here's where the speculation starts to creep in, and it needs to be clearly labeled as such. Some researchers have suggested that interstellar objects might be packaged differently from solar system debris. Not artificially, not as probes or intentional payloads, but as a natural consequence of whatever process ejected them from their home systems. Maybe violent collisions create fragments that are pre-stressed, work-hardened by the impact in ways that make them tougher than rocks that formed gently. Maybe prolonged exposure to cosmic radiation alters their crystal structure. Maybe interstellar space selects for durability, with only the strongest fragments surviving the journey. Or maybe they're just rocks. Strong rocks, well-made rocks, but ultimately just rocks that got ejected from somewhere else and happened to hit us. Without debris recovery, without lab analysis, we're guessing, we're inferring properties from atmospheric entry data, which is like trying to figure out what a car is made of by watching it crash. You can learn some things, but you're missing the details that matter. And that brings us back to the Barents Sea. Because one of these objects didn't vanish into the deep Pacific, where recovery would require specialized submarines and months of searching. It fell onto a continental shelf, into water shallow enough that a research vessel with the right equipment could reach it. The question is whether anyone will try before it's too late. The Barents Sea sits between Norway and the Russian archipelago of Novaya Zemlya, a stretch of Arctic water that's been a fishing ground, a strategic naval corridor, and a contested territorial boundary for centuries. It's not a gentle place. The sea freezes in winter. Ice flows south and then north again with the seasons, grinding against the seafloor, churning up sediment. Biological activity, fishing trawlers, natural sediment transport, all of it works to redistribute anything that settles on the bottom. If CNEOS-22 left debris when it impacted, that debris is already moving. Every current pulls it a little further from the original impact point. Every passing day buries it a little deeper under layers of organic matter and mineral particles settling from the water column above. The impact site is estimated to be in 200 to 400 meters of water, which is shallow by meteor recovery standards. The Pacific impacts that teams have tried to recover material from, like IM-1, sit at depths of 6,000 or 7,000 meters. That's crush depth for most submersibles. That's hours of descent time and complicated logistics just to reach the site, let alone conduct a search. At those depths, you're working in near total darkness with limited visibility, mapping the seafloor inch by inch with sonar, deploying collection systems that might gather sediment for weeks before finding anything useful. The pressure alone makes every operation expensive and risky. Equipment fails, tethers snap, weather windows close. Deep ocean recovery is brutally difficult under the best circumstances. But 400 meters is accessible to commercial, remotely operated vehicles. It's challenging, but it's not impossible. Ships with the right equipment conduct operations at those depths regularly for undersea cable maintenance, resource exploration, environmental monitoring. Oil and gas companies work at comparable depths all the time. Scientific research vessels have ROVs rated for 1,000 meters or more. The technology exists. The expertise exists. If you wanted to search the CNEOS-22 impact zone, you could theoretically mount an expedition with equipment that's already built, already proven, already operating in other parts of the world. You wouldn't need to invent new tools or develop experimental recovery methods. You'd just need a ship, a crew, and permission to work in that specific patch of ocean. The problem is time. Fireball recovery is rare, but it does happen. There have been cases where meteors were tracked carefully enough during entry that researchers could predict the impact zone and search for fragments within days. Fresh impacts are recoverable because the debris field hasn't dispersed yet, because the fragments are still concentrated in a relatively small area, because natural processes haven't had time to bury or scatter everything. If you can get to the site quickly, if you can start searching while the evidence is still fresh, recovery becomes feasible. The Almahata Sitta meteorite, fall in Sudan in 2008, is a good example. Researchers tracked the entry trajectory, predicted the impact zone, and recovered fragments from the desert within weeks. The speed of the response made all the difference. Old impacts, even a few months old, become exponentially harder to locate because natural processes scatter the debris. Ocean currents don't move in straight lines. They eddy and swirl. They shift with the seasons, with the tides, with temperature gradients in the water. A fragment that lands in one spot today might be hundreds of meters away a month from now, carried by currents that researchers can model but not predict perfectly, and that's assuming the fragment stays on the surface of the seafloor. If it gets buried, if sediment accumulates on top of it, then you're not just searching for a needle in a haystack. You're searching for a needle that's been pushed down into the haystack and covered with more hay. In the Arctic, those processes accelerate. Ice drift can move material kilometers from the original site. When pack ice grinds along the seafloor, it doesn't just scrape the surface, it digs furrows. It pushes sediments around. It creates pressure ridges and scour marks that change the bathymetry, that alter the way currents flow, that redistribute anything sitting on the bottom. Seasonal ice advance and retreat happens on a massive scale in the Barents Sea. In winter, the sea surface freezes. In summer, it melts. That cycle drives sediment transport in ways that don't happen in temperate or tropical oceans. Material gets churned, mixed, redistributed. Sediment burial happens fast in active shelf environments. The Barents Sea is not a static, unchanging landscape. It's geologically active in the sense that sedimentation rates are high. Organic matter from plankton blooms, settles constantly. Rivers draining into the sea carry mineral particles. Coastal erosion contributes material. All of that accumulates on the seafloor, building up layers year after year. If CNEOS 22's debris is small, if it broke into fragments rather than surviving as a single mass, those pieces could already be centimeters deep in fresh sediment. They could be spreading across the seafloor right now, pushed by currents, rolled by ice keels, slowly disappearing into the geological record. So why isn't there a recovery mission already underway? Why hasn't some research vessel sailed north to drag the impact zone and see what's there? The answers are complicated and unsatisfying. Cost is part of it. Mounting an Arctic expedition isn't cheap, and without guaranteed results, funding agencies are reluctant to commit resources. You're talking about chartering a ship capable of Arctic operations, which means ice-strengthened hulls and specialized equipment. You're talking about deploying ROVs and sonar mapping systems. You're talking about crew salaries, fuel costs, insurance, logistics. Even a relatively short expedition could run into the millions of dollars. And for what? For the possibility of finding debris that might not even be there, or might be too fragmented to identify, or might have already drifted out of the search zone. Uncertainty is another factor. The impact coordinates from CNEOS data are estimates, not precise locations. The sensors that detected CNEOS 22 weren't designed for pinpoint accuracy. They're optimized for detecting the energy signature of atmospheric entry, not for providing GPS coordinates accurate to within meters. The impact zone could be kilometers wide. You could search for weeks and find nothing, not because the debris isn't there, but because you're looking in the wrong spot. Every day spent searching is another day of ship time, another day of costs accumulating, another day that the debris is moving and dispersing. The longer the search takes, the less likely it becomes that you'll find anything at all. And then there's the classification barrier. Some of the sensor data that would help narrow the search area is still restricted, unavailable to civilian researchers who would need it to plan an effective recovery. The instruments that detected CNEOS 22 are military assets, operated by agencies that don't routinely share raw data with the scientific community. What gets released publicly is processed, summarized, sanitized. The detailed readings that could improve the impact coordinate estimates, that could help model the debris field dispersion, that could tell you exactly where to look, those readings are classified, and without them, you're working with uncertainty that makes the whole mission feel like a gamble. But there's also something else, a silence that feels deliberate. No public announcements from government agencies, no international coordination, no calls for proposals from scientific institutions with Arctic capabilities. It's possible that everyone involved has looked at the situation and decided the odds of success are too low to justify the effort. It's possible that the geopolitical complications of working in the Barents Sea, given current global tensions, make the whole endeavor impractical. The region is politically sensitive. Territorial waters overlap. Military interests complicate civilian operations. Getting permission to conduct a scientific expedition in that area might require diplomatic negotiations that nobody wants to initiate. Or it's possible that someone is already watching, quietly, without public disclosure. That's the thought that sits at the edge of this whole situation. The possibility that a recovery effort is underway, but not advertised. Maybe a government agency with Arctic capabilities and access to classified sensor data has already dispatched a vessel. Maybe they're searching right now, dragging the seafloor, collecting samples, running analyses in shipboard labs without telling anyone what they're doing or what they've found. It wouldn't be the first time a potentially significant discovery was investigated quietly before any public announcement. There's no evidence of a secret recovery mission. None. But the absence of a public mission is striking. If this were a confirmed meteorite fall in an accessible location, there would be researchers scrambling to get there. Museums would be organizing expeditions. Universities would be applying for grants. The scientific community would mobilize because meteorite recovery is valuable, both scientifically and financially. Fresh falls are rare enough that when they happen, people move fast. The fact that the announcement of CNEOS 22's interstellar origin was met with relative quiet, with acknowledgement but not urgency, suggests either widespread skepticism about the claim or awareness of complications that aren't being discussed publicly. Maybe it's not feasible to reach the site before winter ice makes it impossible. The Arctic operating season is short. Once the ice returns, the impact zone becomes inaccessible until the following summer. If the announcement came too late in the season, if the ice is already forming, then any recovery attempt would have to wait months. And by then, the debris will have dispersed even further. Maybe diplomatic issues prevent access. Maybe the debris field modeling suggests that recovery is already too late, that the window closed before anyone could organize a response. Or maybe the debris is sitting there, intact and recoverable, waiting for someone to go get it. And if that's the case, then every day that passes is a day closer to losing the first chance we've ever had to analyze extrasolar material in a lab. The choice we're facing isn't between confirming or denying Loeb's claim. The choice is between acting on the possibility while there's still time, or letting the opportunity dissolve into the Arctic and spending the next decade arguing about whether we should have tried. This is the fork in the road. Either someone goes now, or the moment passes. Either we recover the debris and learn what it can teach us, or we lose it forever and wonder what we missed. And this didn't happen in isolation. In early February 2026, the James Webb Space Telescope released data from its latest exoplanet atmospheric survey, focusing on a super-Earth designated TOI 700G, orbiting a red dwarf star 48 light-years away. The planet had been flagged as a candidate for biosignature detection because its size and orbital distance suggested possible habitability. It sits in what astronomers call the habitable zone, that Goldilocks region around a star where temperatures might allow liquid water to exist on the surface. Red dwarf stars are interesting targets for this kind of research because they're common, they're long-lived, and their habitable zones are close enough to the star that planets there transit frequently, giving us multiple opportunities to study their atmospheres as they pass in front of their host star. What Webb found was unexpected. The atmosphere showed a chemical imbalance, an excess of certain gases that shouldn't coexist in equilibrium unless something was actively producing them. In a lifeless atmosphere, chemistry tends toward equilibrium. Reactive gases combine and neutralize each other over time. You end up with stable compounds, predictable ratios, nothing surprising. But TOI 700G's atmosphere had ratios that didn't make sense. Gases that should have reacted away were still present in abundance. The spectral signatures suggested ongoing production, some process continuously generating these compounds faster than chemical reactions could remove them. On Earth, we see similar imbalances. Our atmosphere is full of oxygen, which is highly reactive and should have disappeared billions of years ago, bonding with rocks and metals in the crust. But it hasn't disappeared because photosynthetic life keeps producing it. Plants and algae split water molecules, release oxygen, and maintain concentrations far above what geology alone would create. The oxygen in our air is a biosignature, evidence of biological activity, that you could detect from light years away if you had a good enough telescope. TOI 700G's atmospheric imbalance isn't the same as Earth's. The gases involved are different, but the principle is similar. Something appears to be maintaining disequilibrium. Not definitive proof of life, but a pattern that didn't fit any abiotic model the researchers tried. They ran simulations. They tested whether volcanic outgassing could explain it, whether photochemical reactions driven by the star's ultraviolet radiation could produce the observed ratios, whether tidal heating or atmospheric circulation or mineral weathering could account for what they were seeing. None of the models worked perfectly. Each one either predicted the wrong gases or the wrong abundances, or required conditions that other observations ruled out. The data stubbornly refused to fit into a non-biological explanation, but it also wasn't definitive enough to claim discovery of extraterrestrial life. They published cautiously, emphasizing uncertainty, laying out the observations and the modeling attempts without making strong claims. But the data wouldn't go away. TOI 700G became an outlier. Around the same time, astronomers tracking fast radio bursts noticed a shift in repetition patterns from one of the most active sources, FRB 2021a. Fast radio bursts are one of the stranger phenomena in modern astronomy. They're intense pulses of radio emission that last only milliseconds, but release as much energy as the sun produces in days. For years after their discovery, we didn't know what caused them. We didn't even know if they were cosmological, happening at vast distances across the universe, or something closer and less energetic. Eventually, observations pinned down their origins to other galaxies, billions of light years away, which meant the energy involved was staggering. This particular burst source had been reliably repeating every 160-odd days since its discovery, a periodicity that suggested some kind of orbital interaction or rotational cycle, maybe a neutron star orbiting a companion, with the radio emission beaming toward Earth only when the geometry aligned. Maybe a magnetar with a precessing spin axis that brought active regions into view on a regular schedule. The periodicity was valuable because it gave researchers a predictable window to observe. You could point your telescopes at the right time and catch the bursts, study them in detail, compare one cycle to the next. But in January 2026, the pattern broke. The bursts started arriving at irregular intervals, sometimes clustered together, sometimes separated by weeks. The source didn't go silent. It didn't fade or disappear. It just stopped being predictable. Bursts that should have arrived based on the established cycle didn't show up. Then bursts appeared at unexpected times, outside the regular windows. The periodicity that had been so reliable, so consistent across multiple cycles, suddenly dissolved into chaos. Researchers scrambled to model what could cause such a change. Maybe the companion star in a binary system had changed its behavior, altering the orbital dynamics. Maybe the neutron star's magnetic field had undergone a reconfiguration, shifting the active regions that produce the bursts. Maybe there was a third body in the system, something massive enough to perturb the orbit on timescales we were only now starting to observe. But none of the proposed mechanisms fit perfectly. Each model explained some aspects of the new behavior, but failed to account for others. FRB 2021. A became an outlier. And then there's the explosion in transient detections, driven by AI analysis of archival survey data. For decades, telescopes have been systematically imaging the sky, taking pictures night after night, building up enormous archives of observations. Most of those images were processed by automated pipelines looking for specific kinds of events. Supernovae, asteroid detections, variable stars. Anything the algorithms were trained to recognize got flagged and followed up, but the vast majority of the data was never examined in detail by human eyes. There simply wasn't time. There were too many images, too many pixels, too much information for people to look at individually. Machine learning algorithms trained to spot anomalies in telescope images started flagging objects that had appeared and disappeared in old observations, events that happened years ago but were never noticed because no human looked at that specific patch of sky at that specific time. The AI wasn't looking for supernovae specifically, or asteroids specifically. It was looking for anything unusual, anything that changed between one image and the next in ways that didn't match the expected behavior of known astronomical objects. And it found things. Some of these transients matched known categories, supernovae, or variable stars that had been missed during the original survey. Those were valuable finds because they added to our statistical understanding of how often these events occur, improving population models and rate estimates. But others didn't fit. They brightened and faded on timescales that didn't match stellar physics. A typical supernova brightens over days, peaks, then fades over weeks or months. These objects brightened in hours and disappeared just as fast. Their spectral features, when archival data existed to analyze them, suggested chemistry we don't fully understand. Elements in unexpected ionization states, emission lines that didn't correspond to known atomic transitions, temperature estimates that seemed impossibly high or strangely low. They became outliers. These three developments, the Webb atmospheric anomaly, the FRB pattern disruption, and the AI-discovered transients, are not causally related. There's no mechanism connecting them. There's no reason to think that TOI 700G's atmosphere has anything to do with FRB 2021A's timing irregularities, or that either of those has any connection to transient objects hiding in archival telescope images. They're separate phenomena studied by separate teams using separate instruments, investigating different questions in different subfields of astronomy. Any attempt to link them causally would be pattern seeking without evidence, conspiracy thinking dressed up as hypothesis. But they share a theme. They're all cases where observation has outpaced theory, where the data shows something our models struggle to explain. We have the measurements, we have the observations, we can see what's happening, but we can't quite account for it with our current understanding of physics and chemistry and astrophysical processes. And they all happened within a few weeks of each other, creating a moment in early 2026 where astronomy felt like it was straining against the limits of what we thought we understood. This isn't the first time astronomy has entered a phase like this. The discovery of pulsars in the late 1960s created a similar moment, a flood of detections that didn't fit existing models. When Jocelyn Bell Burnell found the first pulsar signal, it was so regular, so precise, that the initial reaction was to wonder if it might be artificial, a beacon from an extraterrestrial civilization. They even nicknamed it LGM-1 for Little Green Men. Eventually, the physics community figured out that these were rotating neutron stars, stellar remnants spinning rapidly and beaming radio emission like cosmic lighthouses. But for a while, before the theory caught up, pulsars were just weird signals that nobody could explain. The same thing happened with gamma ray bursts in the 1990s. Satellites designed to detect nuclear weapons tests kept picking up intense flashes of gamma rays from random directions in space. They couldn't be nuclear explosions because they were coming from beyond Earth. They couldn't be from the sun because they came from all over the sky. For years, nobody knew what they were. Theories ranged from colliding neutron stars to exploding primordial black holes to massive stars collapsing into black holes at the end of their lives. Eventually, better observations and improved modeling showed that gamma-ray bursts were indeed from stellar catastrophes, the most energetic explosions in the universe, aside from the Big Bang itself. But during the years of uncertainty, they were outliers. With exoplanets in the early 2000s, the pattern repeated. The first exoplanets discovered were hot Jupiters, massive gas giants orbiting incredibly close to their stars, completing orbits in days instead of years. This made no sense according to planet formation theory. Gas giants were supposed to form far from their stars, where temperatures were low enough for ice to condense. They weren't supposed to exist in tight orbits where surface temperatures exceeded 1,000 degrees. Yet there they were, showing up in survey after survey. Eventually, theorists developed migration models, showing how planets could form far out and then spiral inward through gravitational interactions. But for a while, hot Jupiters were just impossible objects that somehow existed anyway. Astronomy goes through cycles where technology opens a new observational window, and for a while, everything we see through that window is weird. Eventually, the models catch up. Eventually, we figure out what we're looking at. And the anomalies become categories. Pulsars became a well-understood class of neutron stars. Gamma-ray bursts became mapped to specific stellar death mechanisms. Hot Jupiters became integrated into planet formation theory. But in the moment, during the transition, it feels like the universe is misbehaving, like the rules we thought we understood are breaking down. And that's the context CNEOS 22 and CNEOS 25 arrived into. Not as isolated claims, but as part of a broader pattern where outliers are piling up faster than explanations. Astronomy in February 2026 isn't in crisis. It's in triage. The field is sorting through an overload of data, trying to decide which anomalies are instrumental errors, which are genuinely new phenomena, and which are just rare events that we finally have the sensitivity to detect. This is what happens when you build better telescopes and train better algorithms. You find more things, and some of those things don't make sense yet, which brings us back to Earth. We've always thought of Earth as an observatory, a platform we use to look outward and study the universe. Our telescopes point up. Our spacecraft launches away. We send probes to other planets and robots to other moons, because we assume that if we want to learn about the cosmos, we have to go out there and get the information ourselves. And for most of history, that's been true. The universe doesn't come to us. We go to it. Except that's not entirely accurate. The universe has been coming to us the whole time. We just weren't paying attention. Every day, thousands of tons of extraterrestrial material fall to Earth in the form of dust and micrometeorites, tiny particles from asteroids and comets that burn up in the atmosphere or settle gently onto the surface. We breathe it. It accumulates in polar ice. It drifts to the ocean floor. Most of it is solar system material, debris from our own cosmic neighborhood. But statistically, some fraction of it has to be interstellar. If interstellar objects pass through our system, and we know they do, then they shed material. Those fragments, they leave trails, and some of that material ends up here. What CNEOS 22 and CNEOS 25 represent, if the analysis holds up, is a different scale of the same process. Not microscopic dust, but meter-sized fragments. Not passive accumulation, but energetic impacts. These aren't objects we detected at a distance and studied remotely. These are objects that delivered themselves to our doorstep and interacted with our planet directly. If fireballs are the delivery mechanism, then Earth isn't just an observatory. It's a sampling station. It's a collector sitting in the middle of the galactic flow, accumulating material from sources we can't even see. This reframes the entire search for interstellar visitors. We've been looking for the big ones, the Oumuamuas and the Borisovs, because those are the ones our telescopes can spot. But those objects are statistical outliers. They're rare. For every kilometer-sized interstellar comet that passes through our system, there could be millions of smaller fragments, too small to detect optically, but large enough to survive atmospheric entry and leave debris. We've been focused on the exceptions while ignoring the common case. If that's true, if interstellar material is being delivered to Earth regularly at small scales, then the implications are significant. It means the exchange of matter between star systems isn't some exotic edge case that happens once in a blue moon. It means it's continuous, ongoing, a background process that's been happening throughout Earth's entire history. It means that when we study meteorites in labs, some fraction of them, maybe a very small fraction, but not zero, might have extrasolar origins, and we just haven't noticed because we weren't looking for the right isotopic signatures. But we still don't know for certain. That's the frustrating part. The analysis of CNEOS 22 and CNEOS 25 is strong, but it's not settled science. The velocity calibration is robust, but calibration models can have unknown systematic errors. The trajectory simulations are convincing, but simulations depend on assumptions about atmospheric physics that might not hold at extreme entry speeds. The strength characteristics are unusual, but unusual doesn't necessarily mean interstellar. Until someone recovers debris and measures it directly, until we have isotope ratios and mineral compositions that can't be explained by solar system formation, this remains a high confidence inference, not a confirmed fact. And that leaves us with two possible endings. In one version, CNEOS 22 and CNEOS 25 are exactly what the analysis suggests: fragments from another star system that survived the journey across interstellar space, only to burn up in our atmosphere and scatter across the Arctic seafloor. If that's true, then we've massively underestimated the rate of interstellar material exchange. We've been thinking of it as a rare event when it's actually common. We've been looking in the wrong places, at the wrong scales, for the wrong things. And the correction to our understanding would be enormous. In the other version, there's some subtle error in the analysis, some overlooked factor that makes these objects appear interstellar when they're actually not. Maybe the velocity calibration model has a blind spot. Maybe the atmospheric entry dynamics are more complicated than we thought. Maybe the objects are solar system members with extremely unusual orbits that happen to mimic interstellar trajectories. If that's true, then this becomes another cautionary tale about the dangers of overinterpreting limited data. Another reminder that extraordinary claims really do require extraordinary evidence. But here's the thing: either outcome changes something. If these objects are interstellar, we've discovered a new channel for studying extrasolar material. If they're not, we've learned that our detection and analysis methods need refinement, that we can't trust fireball data the way we thought we could, and that's valuable information too. Science doesn't just advance when we confirm hypotheses. It also advances when we rule them out, when we identify the boundaries of what our tools can actually tell us. Right now, in February 2026, we're in the uncertain middle. The analysis says interstellar. The skeptics say maybe. The debris sits somewhere in the Barents Sea, possibly recoverable, possibly already lost. And the rest of the scientific community watches to see what happens next. Whether someone will mount a recovery effort, whether new data will strengthen or weaken the claim, whether this becomes a paradigm shift or a footnote. We keep looking outward for answers, while the answers may already be melting into the ocean beneath us.